Okay, so this is a set of notes on the determinants of a matrix. The basic idea here is that we need a quick way to determine whether or not a matrix has an inverse, and we're going to use a metric to do that. So we're going to boil a matrix down to a single number. If that number happens to be 0, then we know that the matrix is singular and it does not have an inverse. If that number is something other than 0, it will end up having an inverse. So we want to form a metric that'll do that. Now, doing that for 2 by 2 is fairly easy. The idea here is it's the coefficient in front of the inverse formula for 2 by 2's. So literally, if I have some matrix A that's 2 by 2, and I have this as A11, A12, A21, A22, then my determinant of A, so we can either write it as the determinant of A or the determinant of A, is A11 times A22, so it's like down on the diagonal, minus, and then we go up on the diagonal, A21 times A12. Okay, so like if I want to take the determinant of 2, negative 3, 1, 2, this is 2 times 2 minus 1 times negative 3, which is 8 plus 4, which gives me, sorry, that's not correct. This should be not 2 times 4. I got ahead of myself there. It should be 2 times 2. There we go. Minus 1 times negative 3. That's a little better. Which is 4 plus 3, which is 7. And according to what we've said here, because this is 7 and 7 does not equal 0, we actually know that this matrix has an inverse. Okay? So how do I deal with this if it's larger than 2 by 2? Well, then we get into a problem of recursion here. Okay, so we're going to define something that we call the minor of the matrix. Okay? So we're going to let A be an n by n matrix, and we're going to define something here. We're going to call minor ij is the determinant of the A matrix without the J column. So in that row, we got rid of the J column. It's straight from J minus 1 to J plus 1. And we're going to do that every row. And then what we're going to do is we're also going to get rid of the ith row. So this is the I minus first row, and then we're going to jump right to the I plus first row. So the minor is the determinant of the A matrix, I plus 1, J minus 1. So it's the determinant of the A matrix without the ith row and without the jth column. And that would give me what we're going to call the ij minor. So let's get this last row in here. an1, an2. Right, so this will be ai plus 1. No, that's not correct. It's an j minus 1. This one is going to be an j plus 1. And then this will be an n, because this is a square matrix. So the minor is the determinant of this thing. So this is the ijth minor of A. So why do we care? Okay, so the next iteration in this is we're going to come up with what's called a cofactor. So I want to define a cofactor. So if A is an n by n matrix, right? And then we're going to let Cij be -1 to the I plus j. So that's just going to be a sign iterator, right? So if I go down a row, it's going to go positive, or down a column, it's going to go positive, negative, positive, negative. If I go across the row, it goes positive, negative, positive, negative. And we're going to multiply that by the minor. So this is the sign, this is the minor. So now this begs the question, right? So Cij is the ijth cofactor of A. This begs the question, why do I need a cofactor, right? So the minor is part of the cofactor. It's just a signed minor. And then once I have the cofactor, I can expand by cofactors and end up with a determinant. So this is going to give us a definition for a determinant for matrices larger than 2 by 2. Now, the idea here is this is recursive. So we're just going to say that A is an n by n matrix. Then the definition of the determinant is actually very simple. It is the sum from j equals 1 to n of the cofactors of the first row. So the values of the first row of the matrix times their cofactors. Okay, so I'm going to basically take the first row. Oh, that should be 1 as well. Take the first row of the matrix. I'm going to take all the values. I'm going to multiply them by their cofactors and create the determinant. Okay, so why is this recursive? Because the cofactors of a 3 by 3 matrix have a determinant of a 2 by 2 in it. The cofactors of a 4 by 4 matrix have the determinant of 3 by 3s. To find the determinant of 3 by 3s, you have to take a determinant of 2 by 2s. And luckily for us, we have a way to do 2 by 2s that doesn't require this definition. So we can get out of the recursion. So let's give an example of this. Okay, so let's say I want to take the determinant of the matrix 0 to 1, 3, -1, 2, 4, 0, 1. Okay, so let's take a look at that guy. Alright, so let's expand by the first row here. So this is going to be 0 is A11. Now I have to look at the minor of that, right? So its minor is going to be the determinant of -1. Oh, sorry, I need a cofactor. So wait, this is 1, 1. So this is going to be I, -1 to the 1 plus 1, which is squared. Now times the determinant of the minor here is -1, 2, 0, 1, because I've taken out the first row and the first column to go with 1, 1. Alright, so now I take 2 times -1. Let's see, this is in the 2, 1 position, so it's going to be cubed. times its minor, which is going to be 3, 2, 4, 1. And then we take 1 times negative 1 to the 4th, because this is in the 3, 1, or 1, 3 position. 1 plus 3 is 4. And then we go 3, negative 1, 4, 0 is its minor. Okay, so here, 0 times anything is 0. Now, let's see, this is going to be minus 2 times, the determinant of this is 3 minus 8. And then this is going to be plus 1 times 0 plus 4. Let's see, that's 0. This is negative 5, so that's 10 plus 4 makes the determinant 14. All right, so with a little bit of recursive work, you can get the determinant of a 3 by 3. 4 by 4 requires more recursion. You can see where after a while you're not going to want to be able to do this by hand. You could, I mean, like you can expand like a 16 by 16 matrix and do it by hand, but it doesn't seem very fun. All right, there is a trick to 3 by 3s, and I'm going to demonstrate that in the next frame. Okay, there is an easy way to get the determinant of a 3 by 3 matrix. So let's say I have a matrix here, 0, 2, 1, 3, negative 1, 2, 4, negative 4, 1, and I want its determinant. Now we've seen this trick before. We saw it in ACalc, but we used it for something like the cross product. But let's take a look at what we're doing here. What I'm going to do is I'm going to repeat the first 2 columns. And then I'm going to go down on a diagonal. So let's say I have 0 times negative 1 times 1, that's 0. 2 times 2 times 4, so it's 2 times 4, 16. And then, let's see, that's going to be negative 12. And now I go up, but every time I go up, I'm going to make it negative. So this is negative 4, so I'm going to add 4. This is 0, so I'm adding 0. And this is positive 6, so I'm subtracting 6. So let's see what I have here. 16 plus 4 is 20. 20 minus 12 is 8. 8 minus 2 is, or sorry, 8 minus 6 is 2. So the determinant of this is 2. Now you can go and you can take a look and see how that works out with a cofactor formula. It does exactly what you would expect it to do. So that's a little bit of a trick that only works with 3 by 3 matrices. Okay, so we have upper and lower triangular matrices, which actually have a very easy determinant to compute. So an upper triangular matrix is going to have values down the diagonal, values up here, and then everything below the diagonal are going to be zeros. A lower triangle matrix has values down the diagonal, values here, and everything above the diagonal is going to be zeros. So this is upper triangular, this is lower triangular. Now, the determinant of this is like the easiest thing in the world. If you take a look at this carefully, you can see that if I have an upper or lower triangular matrix, the determinant of the matrix is actually the product from I equals 1 to n of the diagonal entries, A, I. Okay, so let's take a look at an example of this and what we mean. So let's say for a minute I have 2, 0, 0, 0, 4, negative 2, 0, 0, negative 5, 6, negative 1, 0, 1, 5, 3, 3. Now, if this was not a lower triangular matrix, I would never want to have to expand this by hand. Imagine doing a 4x4 with cofactors. But because all of this is zeros, everything above the diagonal is zeros, I only have to take the product of the values going down the diagonal. So let's see, 2 times negative 2 is negative 4, times 1 is 4, times 3 is 12. And there you go. I have the determinant. Should be 12. Yep, there we go. All right, so that's it for that. Let's get a set of properties here for the determinant. We have 5 of them. If I take the determinant, the determinant of the product, I get the product of the determinants. That works out nice. Number 2, if I take the determinant of a scalar times a matrix, it's equal to the, this is a little bit tricky here, it's equal to the scalar to the nth power times the matrix, okay? So that's because that scalar gets played out in each of the cofactors as you go along in the expansion. This is the important one. If the determinant is not 0, this is if and only if A is invertible. That's the one that's most important because that's why we built it in the first place. If I take the determinant of the inverse, that's 1 over the determinant. And lastly, if I take the determinant of the transpose, it's just the determinant of the original matrix, because remember, expansion by the cofactors doesn't only have to be done by the first row. It can be done by any row or any column of the matrix. So if I exchange the first row for the first column, I'm still going to get the same expansion of cofactors. All right, so there is your material on determinants of matrices.